So I don't know what a masterclass is, and so this is what I decided. It seems this has two parts, is that right? So the first part, I'm going to tell you what neutrino astronomy is, and I'm going to tell you about how you build a neutrino telescope. Then we actually discovered something, but that I won't tell you about. You can either read it in Science, or you can come to my talk tomorrow. What I'm going to do instead in the second half is talk about the science we do that I will not talk about tomorrow. So I'll do everything I know except what I talk about tomorrow, which is admittedly the most interesting thing. You don't have to come to my talk tomorrow. I'll give you a little preview. So don't worry. Now, so this is the first half of the talk. So the first half. So I want to talk about cosmogenic neutrinos. It doesn't matter if you don't know what this is, I'm going to tell you. Then I'm going to tell you about cosmic rays. Then I'm going to tell you that somehow neutrinos are connected to cosmic rays. And the important part of this is that if you want to do astronomy with neutrinos, this discussion will tell you that you have to build a kilometer-cube neutrino detector. It's very important for me to explain this because, you know, if you tell someone you actually have built a kilometer-cube neutrino detector, they think you are crazy. So I'm going to tell you the logic, the rationale behind this. And then I'm going to tell you about the detector we built. And then I will tell you how that we discovered cosmic neutrinos. And that's what the detector was built for, but that's the talk tomorrow. But if you cannot come to my talk, I'll give you a small preview. You can sleep late. So what's special about the neutrino? Special about the neutrino is that it has no electric charge. When you go out at night and you look at the stars, the reason you do astronomy with your eyes is because light travels in straight line to your eyes, and so you detect the direction of the photons, and then your brain makes a pattern, which is what you see. You can only do that if photons had an electric charge, which is very, very forbidden, but I know that. But if they had an electric charge, before they would reach you, they would come through the magnetic field of the galaxy, and they would just, you know, go in all directions. They would be bent. Our galaxy has a 3 microgauss magnetic field, which is pretty strong. And so it's impossible to do astronomy with charged particles. I mean, we detect protons from outside the galaxy, but they don't tell us where they come from. By the time we detect them in cosmic ray experiments, they come from everywhere. They are isotropized by the magnetic field in the galaxy. And so you can only do astronomy with neutral particles. So what is that? Is the neutron. But the neutron doesn't live long enough. In fact, only at very, very high energy could you, in principle, for instance, people have been looking for neutrons arriving from, it lives 1,000 minutes. But if you use the Lorentz boost of a very high energy proton, like at 1,000,000 TeV, then it can reach us from the center of the galaxy. And so, but they have not been seen. So that's a problem. You cannot see very far, and you can only see them when they have extremely high energies. So the neutrino was proposed as a way, you know, it looked like when a neutron decays, it decays into a proton and an electron. And so people discovered when the proton goes this way, if I'm the neutron, the electron goes that way. And people found that they saw decays like this of the neutron. Of course, it means some other particle goes the other way. And that was the neutrino. That was, in fact, this is what's called the missing energy measurement. So by today, we discover a lot of particles in the last decades by doing missing energy measurement. So by the definition of today, the people who did these experiments, Ellis, for instance, at the Cavendish, they would have discovered the neutrino. But they never thought, at the time, only the neutron, the proton, and the electron existed. In fact, I'm not sure the neutron already existed. The neutron did exist. The positron didn't exist. So they never thought that this was a new particle, except Pauli proposed it was a new particle. And so this is a long story. It took about 30 years before Reines discovered the neutrino and detected neutrinos from a nuclear reactor. And Reines told me, he died not so long ago, he told me that as soon as people realized that this was not some mathematical concept in field theory or of beta decay, that this was a real particle, everybody immediately had the idea of doing neutrino astronomy. So it's an idea that's around since 1956, and according to him, everybody had the idea. So that's the idea. There's nothing new. The key, of course, for these discussions is why do you need a kilometer-cube neutrino detector? And so that's what I'm going to go into. So let me start with this slide. This is an amazing slide. We have to spend some time on it. First of all, the slide is 25 years old. It's a slide I've been carrying with me since I started in this business. And it's the right slide in the sense you don't get into the latest updates of the details in this slide. It's just a cartoon. And so this slide tells you if you have a telescope and the telescope has a certain size and it works at a certain wavelength, it tells you how many photons you detect. So if you have a microwave detector, you see the microwave background, and you see there this peak that tells you how many photons you detect. So this is the diffuse flux of light throughout the universe. In fact, you can also think of it as what the energy density per cubic centimeter is. I'll calculate for you in a minute. In microwave background throughout the universe. Of course, the universe is filled with radio waves. There are less of them. That's this. This is how much visible light there is. So if you go out with a mirror, this is how many photons you detect. And you see this slide stops at, that's 10 GeV, which is about 10 to the minus 14 centimeters square in wavelength. And so those photons are detected by satellites that have to fly above the atmosphere. And so the detectors are that big. And so we actually don't know whether this flux continues or and that this is just due to the fact that satellites have a limited size, and so you just run out of flux. You have to realize, if you look at this slide, right, I'm now talking about 10 to the minus 8, and we start at 10 to the 12. Right, so these are 20 orders of magnitude. So you have only one photon anymore for every 10 to the large number of microwave photons. So now people have, and this is part of my talk tomorrow, people have looked for photons of high energy. I'm going to use as my natural unit in this talk 1 TeV. That's my small unit. 1 TeV is 10 to the 15 electron volts, so it's somewhere here. And so I'm going to talk in multiples of TeV. TeV is the energy of the tevatron at Fermilab. The LHC beam is 7 TeV, so that's the small unit in this talk. So the idea is kind of we have never seen like 1,000 TeV photon. And there's no reason we haven't seen it, that I know, because you can detect 1,000 TeV photon with an air shower array. And people have built lots of air shower arrays. So the normal particle detectors that people build to detect cosmic rays can detect photons. And so if there were a flux here, it would have been seen. So what this means is below this level, which is actually quite interesting and has something to do with neutrinos. But so the idea was to just do neutrinos like from 10 GeV to infinity. The higher energy a neutrino is, the easier it is to detect it, because the neutrino cross-section grows with energy. And so if you go to high energy, it's more likely to interact inside your detector, and it's more likely that you see it. So it's very beautiful. High energy here is easy. It's the other way around as from cosmic rays. So, you know, is there anything in the universe at these energies? And of course there is. You can see that here. This is like a cartoon again of the cosmic ray flux. So these are, you detect. So if you have a detector here, you don't detect photons, you detect cosmic rays. And so these are protons mostly. So I will generally talk about them as protons. There are in different places other nuclei, but that's not relevant in this talk. And people actually have seen TeV photons, but we don't really know what their flux is, but we have seen individual nearby sources. And this is pretty interesting, and I come back to that discussion. By the way, you can interrupt me, right? I'll stop from time to time to ask for a question, but you can interrupt me anytime. If I say, I do say things that I should say and forget to say, so. Okay, so what does this have to do with neutrinos? And here is our first exercise, which is extremely easy. You've first noticed that these cosmic rays have an energy of about 10 to the 8 TeV. So they have 10 million times the energy of the LHC beam. That's a lot of energy. So there is this big universe, and in this universe are these protons, and there are those photons. So whenever a proton meets a microwave photon of this energy, it actually can produce a pion. So the collision energy allows you to produce a pion. And this pion will decay into a neutrino. And so that's a cosmic neutrino flux. We see neutrinos from the sun and from the atmosphere, as I will tell you in a minute. But this is an interesting neutrino. This comes from the cosmos, and it's produced by a cosmic ray. So the hope is if you see that neutrino, it will point back to where cosmic rays are living in the universe. And this is, the holy grail of cosmic ray physics, is find the sources. We've been trying to do this for 101 years now, unsuccessfully. And so you can calculate how many neutrinos you would see, because we know what the cosmic ray flux is. It's been measured. It's on that slide. We know the microwave background, 410 photons every cubic centimeter. We know the interaction cross-section for photons and protons, since 1950 actually. So you can it's a one line back of the envelope that will tell you how many neutrinos you see. And the answer is given on the next slide. So the bottom line is that you see one event in a kilometer-cube neutrino detector per year. But you know, in the 70s, these arguments go back to the early 70s, and it may be that you solve the cosmic ray problem with one neutrino. So people started in the early 70s to try to build a kilometer-cube neutrino detector. We finally managed to do this in 2010. So it was a long way. But you know, in neutrino physics, the natural timescale of anything happening is 20 years. So this is nothing unusual. But that's the bad news, kind of. You know, you wish it were 1,000 rather than 1. But there is good news. What happened? This pion, you know, has this enormous energy because you don't produce it in the center of mass. The proton hits this microwave photon, and the pion comes out with huge energy. And then what it does, it decays. It decays into a muon and a muon neutrino. That's one you're looking for. And then the muon decays into an electron, a nu mu, a nu e, and then this is... So basically the pion that moves with huge energy gives this energy to 4 leptons, an electron and 3 neutrinos. And so you can just take the energy of this pion, and we'll do this from now on, and divide it by 4, and that's your neutrino energy. And so if you work through all this, you find that the energy of this neutrino is 10 to the 18, which in my units, a TeV is 10 to the 12. So it's 1,000,000 TeV. So this is an enormous energy neutrino. And it may be only 1 a year, but you cannot miss it, as you will see with the instrument we have built. Okay, so now this is 2013. I know this paper is the last calculation done last year. And so here you see, this is the professional version. Here is this tail of cosmic rays that above threshold. So you take this data, you take the particles, you collide them with the microwave background, and this green band are the neutrinos that come out. The prediction is actually this green line. The green band are kind of the astrophysical ambiguities. And you see, this is not the subject of this talk, but this green line in IceCube corresponds to 2 events per year. We haven't seen any yet. But then, you know, this is a logarithmic scale, so it'll take us a couple decades to get to the bottom of this green band. So it's only the beginning that we are sensitive to. So anyway, but also Auger is sensitive at a similar level, and some radio experiments that are being built now. So,
sorry,
yeah.
How long does this neutrino travel before it reaches the Earth?
Wherever it's produced, it comes at the speed of light. By the way, neutrinos travel at the speed of light here. We are at such high energies that the mass doesn't matter. So just like a photon. So you tell me the distance, and that's how many light years it takes to get here.
But on average, you can predict it?
No, it depends where the sources are. Right? So imagine here is a source, and it may be, you know, 10 kiloparsec away if it's the center of the galaxy. It may be a gigaparsec away if it's some black hole somewhere. And then it just takes light speed to come to here. Yeah, it's a long time still. Yes?
Just a follow-up to this question.
Yeah.
Are these sources all extragalactic or within the Milky Way?
Both. So the cosmic ray problem is actually 2 problems. This tail is extragalactic. How do I know it's extragalactic? Well, if you can calculate, remember our galaxy, you think of as a bottle that has a 3 microgauss field. So if the gyro radius, so a charged cosmic ray, will sit in this magnetic field and have a gyro radius. And in fact, if it's like 1 TeV, it will just gyrate in this bottle for 1,000,000 years, and then it may escape. If the gyro radius at these energies, that's why I use these neutrinos, is larger than the size of the galaxy, so it's not contained. So as soon as you come to this gyro radius, then you know that you are looking at an extragalactic component. So actually, the cosmic ray problem is 2 problems. Where do the galactic cosmic rays originate? Where do the extragalactic cosmic rays originate? We don't know the answer to either question, but we'll know soon, hopefully. We'll see. Okay, so let me now talk about the cosmic rays themselves, because they give you some very interesting. You may say, how do you accelerate particles in the universe? Remember, these are enormous energies. How, look what it takes to build the Tevatron and the LHC, and now you get 10 million times more energy. Where does this come from? And so I'll lead you into answering the question. As I said, we don't know the answer. What you are looking at here is the sun. And this is a solar flare. So what happens during a solar flare is these filaments you see, this hair, those filaments are streams of relativistic particles. So if you have a moving relativistic particle, it makes a magnetic field. So there are magnetic fields where these filaments are, and so the particles get accelerated. I won't go into how this happens. This is black magic. It goes under words like shock acceleration, reconnection. If something has 2 words to explain, it means that we don't know. And so actually solar flares are pretty well understood, but not what I will talk about next. Anyway, so we see these cosmic rays. Protons are accelerated all the way to 10 GeV. And we see 10 GeV protons from the sun arriving at Earth. So why 10 GeV? Well, there is a very simple and nice argument for that. Suppose you have an accelerator like a solar flare. You accelerate, it's okay. You want to accelerate a particle to an energy E in a magnetic field B. So B here is the magnetic field where the solar flare happens. And so the gyro radius of that particle is E divided by B. Now, of course, VQ, Q is protons, is 1, and V is the speed of light. Everything in this talk moves at the speed of light. So the gyro radius must be smaller than the size of the accelerator. In other words, the proton that's accelerated in the solar flare must have a gyro radius which is smaller than the solar flare. If it's bigger, it's not contained and it cannot be accelerated. It's just simple common sense. So you see that equation E over B is smaller than R, which I can write as E is less than B times R. And if you put in for B here the magnetic field of the sun where the flares happen, which I have forgotten what it is, but it doesn't matter. You put in here this typical size of a solar flare, you get here 10 GeV. And this is not physics, well, this is dimensional analysis. You cannot violate this formula. And, it's very difficult actually to find anything in the universe you can even think of that satisfies this equation. But this equation, for instance, if you put here in 1 Tesla and here 4 kilometers, you get 1 TeV. You also have to remember that the beam goes around 10 to the 5 times per second. So the Tevatron satisfies this formula, the LHC beam too. But there you have engineers lining up magnets. Can you imagine someone doing this somewhere in the universe? I cannot, maybe it's true, that's where they come from. But you see you cannot violate this formula, and we can only think of a handful of objects that will get you in the galaxy to 1,000 TeV, and outside the galaxy to this 10 million TeV. You know, it's an incredible challenge. So, but that's the easy part. Here is the hard part. If you think about the energy in these particles, you know, experimentalists will tell you how difficult it is to detect cosmic rays because they see 1 per kilometer square per century. That's an experimental problem. That's the wrong way of thinking about it. Let's do the microwave background. 410 photons, 2.7 degree Kelvin per cubic centimeter. That is an energy of half an electron volt per cubic centimeter. So everywhere in the universe, in every cubic centimeter, there is half an electron volt of energy. And now I'm going to do the same calculation for the galactic cosmic rays. So as I already explained, these cosmic rays are galactic, and then somewhere here, they become extragalactic. So if I here, I add up the particles with their energy, I actually get the same number. So in our galaxy, I think that's an accident, but there is the same amount of energy in cosmic rays as in microwave photons. There is also the same amount of energy as in magnetic field. If you add up all the light in our galaxy, it's the same energy. So light, magnetic field, cosmic rays, they all tend to the same energy density. That means that cosmic rays actually, they are not some rare object, some rare occasion. They are part of the life and equilibrium of the galaxy. And actually, it turns out to be very difficult to think of sources that can generate this energy. So in other words, my first slide says you need a strong enough accelerator to get to the highest energy. This slide says it better have enough luminosity to explain what we see, and that's not easy. So now if I do this calculation for the extragalactic cosmic rays, I get a smaller number, 10 to the minus 19, but this now is per cubic centimeter, not in our galaxy, but in the whole universe. And again, this is so much energy in particles. So the bottom line is between these two slides, there is no good idea left. And so I'm going to show you the ideas that people are trying to make work. But it's really theory here is an act of desperation. So what do we make that's bigger than the sun, has more magnetic field? To get above this 10 GeV, remember you have to get to 1,000. This is a picture of a supernova remnant. So 1,000 years ago, a star exploded here, collapsed. And the gravitational energy is released in the interstellar medium. And so you see here the debris of the star. And just like in a solar flare, streams of, after 1,000 years, you see these filaments. This is an X-ray picture. That's where very fast moving streams of particles are. They are powered by the gravity from the star that collapsed. And so it's exactly the same thing. That's where cosmic rays are accelerated. If you now do the Hillis formula, and you calculate the energy in this, it works. You can get like maybe to 1,000 TeV. And with 3 supernova explosions per centimeter, you can produce the cosmic rays we see in the galaxy. Provided about 10% of the energy in the explosion goes into accelerating particles. 10% is probably a large number, but we don't have a better idea. This is it. Okay, so what do you do? Now I'm going to digress for a Where are the neutrinos? Well, this is a very beautiful example. Okay, this is a cartoon. So your supernova remnant explodes. So here in these regions are very energetic particles. Now, where do supernovae explode? They explode where stars are formed in the first place. So you look at star-forming regions in our galaxy, and there you see the supernova explosions. But why is it a star-forming region? It is because it's a region where stars form, so there's high mass concentration. And so there are, among other things, molecular clouds in star-forming regions. So whenever this expanding accelerator, the accelerated particles meet a molecular cloud, you have a beam, what particle physicists call a beam dump. You have a target. On the target you produce pions and you get neutrinos. And so does this happen? Well, this is a map of our galaxy in 10 TeV gamma rays. This is a very unusual map of the galaxy, but it looks exactly like other maps of the galaxy. You see the galactic plane and not much else. And so this is the Cygnus, the star-forming region in Cygnus. And so if you look at detail, the strongest gamma ray source, remember we're talking 10 TeV gamma rays, these are the highest energy gamma rays ever detected, is this source. If you go and look in astronomical catalogs at other wavelengths, you won't find this source. This is a molecular cloud. And so it presumably are pions, neutral pions produced in collisions of the cosmic rays with the molecular cloud that make pi zeros, and the pi zeros decay into 2 gamma rays, which is what they see. And this, of course, now you don't have to be a theoretician, right? If you have proton-proton collisions or nucleus, any molecular cloud collisions, the one thing that's sacred is that you produce equal number of pi zero, pi plus, pi minus. So the pi zero makes 2 gamma rays, the pi plus decays into a neutrino and a muon, and the muon decays further. So the bottom line is that you get a neutrino and an antineutrino for every 2 gamma rays. And so there's no calculation. You know exactly what the flux is you see. And the result is 3 plus or minus 1 neutrinos per year from here. And there are some other sources like this, so maybe 10. Okay, well, I don't know how to count sources. But so we are not far away from 1 per year. It's a bit better. This idea, as I said, it's the only good idea actually around, was first suggested in this paper, 1934. So I think it's time to prove this by seeing the neutrinos. I always joke we'll make this man smile soon. But if you actually go and read the paper, that nobody ever does, including me, I decided 3 months ago to actually read the paper. And he has all the ideas in there, but he actually says that it will be star-forming regions from other galaxies. Because in our galaxy, we haven't seen a supernova since Kepler. And so they're obviously not enough in our own galaxy. Of course, we know now that we don't see most of the supernova that are happening in the center of our galaxy, or where most of the mass is. So anyway, so now we have the sun, we have scaled it up, we understand the galactic cosmic rays, we have one model. There are people who try to make pulsars work, but I don't think this is kosher. So what about the extragalactic? Same idea. So you just have a star that collapses to a gamma ray, to a black hole, instead of a neutron star. And then all the same things happening. I could take my speech over, except instead of in 1,000 years, they happen in a few seconds. But you get the gravitational energy of the collapse to a black hole gets released, and the difference here, I'm showing you simulations instead of real pictures of objects, and you see it's not nicely spherical because the black hole has a spin, and so most of the stuff is moving along the the spin direction of the black hole. But and you work out the Hiller's formula. You say that 1 to 10% of the explosion in the gamma ray burst goes into cosmic ray acceleration. You have a model. And that's it. We have one model for each, except there is, now here you don't even have to, you have to know any theory. So fortunately, I mean, for neutrinos, in this explosion, there are protons because that are the cosmic rays eventually. Then there are photons because the photons are radiated from electrons. These are the photons that the astronomers see. So again, it's a case where you know the cosmic ray flux, you know the photons by looking at the astronomical observations, and you have protons and photons in the same place, you make neutrinos. Same idea, but now it's even easier to do the calculation. Remember, this is the reaction. These are the cosmic rays. These are the photons in the fireball from the gamma ray burst. Now, what happens in a gamma ray burst, after the star collapses to a black hole, the stuff actually is opaque. It's not transparent to light. So the fireball, what they call the fireball, has many light interaction lengths. So what it does, it expands under radiation pressure. There's no other way it can lose energy. It cannot emit because it's opaque to photons. So it just under radiation pressure expands. While it expands, the acceleration is happening, but the protons are trapped. They don't get out either. And by the time the fireball becomes transparent, that's when the astronomers see it. The light finally gets out. But the protons by then have lost their energy. So you don't have a proton machine. However, when the protons live in the fireball, they can become neutrons. And the neutrons are neutral. They can come out of the accelerator and they will decay. And so all the cosmic rays we see in this model were born as neutrons that decay on their way here. And of course, for every neutron, you have a pi plus that gives you the neutrinos. And so you can just immediately transfer the proton data and neutrino data. Okay. So this is an active galaxy. So what it means, it's a galaxy, but unlike it has an enormous active black hole. Ours has too, but it doesn't have an active black hole. And so you can actually make a model out of, the game is to satisfy my 2 slides, right? You can actually make a model out of this for that works, that satisfies the 2 slides. So we have 2 models for extragalactic cosmic rays. But so in general, the idea is wherever cosmic rays are born, you have an accelerator and you have a target. And the target, every black hole is surrounded by radiation. So it's just like at CERN, you have a beam and a target, and then the pions, you produce pions, and when they decay, you have a neutrino beam. It's exactly the same. But the target may be made out of light but often like were molecular clouds in the case of supernova remnants. But so the physics is always the same. And you see, the idea is that the protons themselves, they may be trapped in the accelerator, because the accelerator, you have the magnetic field, you have to confine to accelerate them. So the general picture is that they may come out as neutrons. And then you have 1 cosmic ray per neutrino per gamma ray. And if you do the counting correctly, there's a factor of 2 here or there, but we are not worried about that. In fact, the astrophysics is such that you can get you can afford to get a factor 2 wrong. I don't recommend this, but the astrophysics of the systems is such you can afford this. So this is my summary slide. The cosmic rays we are looking for, So this is now a picture of the cosmic ray flux, a professional picture. And so you see here on the left, that's where the sun, we are not interested in this, produce cosmic rays. You see this is what's called an E in the spectrum, this turn-off. Those are the galactic cosmic rays. And what you are seeing here is the accelerator running out of steam. You know, it cannot accelerate anymore. These are the extragalactic cosmic rays. And so we have two ideas for this, one for that. And, you know, very few people think these ideas are wrong. There's two remarks. There's no evidence for any of this, none whatsoever. But we've gotten used to it. This is in textbooks, as if it's, you know, we just gotten used to it. And except for here, there are two ideas instead of one. But so the hope is that the neutrinos, you know, a handful of neutrinos, you know where they come from and the problem is solved. We will know. Okay, so this is a good place to ask for questions. Any complaints? Everybody happy? Okay. Yeah, this is not rocket science, right? I mean, this is what it is. Yeah.
What is the rate of how the black hole lose energy? I mean, the accelerator lose energy. What's
Yeah.
the rate? How much?
Here, the acceleration actually, you know, you get the idea that you have to have some kind of gravitational source that creates streams of relativistic particles that create effective magnetic fields. You get acceleration. So the way this works is, on a black hole, the stuff in the galaxy with an active black hole at the center is accreting on this black hole. That gives you a stream of particles. And so that's where presumably you can accelerate cosmic rays. And so how much energy is in that depends on what a black hole is. And actually what happens is black holes, if they typically accrete matter and then they choke. You would think the matter just disappears. It doesn't. They choke and then cannot absorb the matter. Then they blow it off. And that are these jets you see. And these jets are again streams of relativistic particles. So we don't know. But you can make either model work. Acceleration in the jet or in the accretion disk. So, you know, supernova remnants and gamma ray bursts are very simple, clean systems where I can calculate the neutrino flux. In the model of active galaxies, it's very difficult. You don't know where the accelerator is. You don't know what the target is. There's target photons. There are target photons everywhere in an active galaxy. But you have all these combinations you can choose. And so there's no clean prediction like a gamma ray burst that tells you one cosmic ray per neutrino. You don't have to know any physics. Just P gamma goes to n pi plus. Does that answer your question? Yeah, so it's not like the Hawking, nothing fundamental like Hawking radiation or so have anything to do with this, yeah. Okay? Yes?
Just a question for
I rather ask questions than, I have time. It's 8:45. Yeah, is it?
No, it's 20 past 8.
20 past 8.
And then? When does it, then there is a break and then?
The break is 8:45.
The break is 8:45. So now it's 20:8. Thank you, I know that. Okay, yeah. Oh, I thought it's now. I have to stop. Okay, thank you. Yes, sorry.
You said in these active galaxies you produce a neutron and a pi plus.
Yeah.
But we don't see the neutrino from this pi plus, right? Oh.
Yes, that's the one we see.
But
Or we hope to see.
But it is produced within this active galaxy.
That's the beauty of neutrinos. They just get out.
No, but the pion is produced. I mean, if
Yeah, but the pion decays, right? We know the lifetime.
If the proton interacts with the gamma within this active
Yeah, yeah.
active,
Yeah,
and then you have a neutrino, you have a neutron and a pi plus, but the pi plus is within a gigantically large magnetic field, right? I mean, for a short time that it lives, but it sees a really.
oh, but it cannot, it will, you know, in the magnetic field, it can scatter, so, but in practice the lifetime is so short that this pion will just decay.
The size of the source is
Yeah.
bigger than the distance of the source.
Yeah. This accelerate, remember we're talking black holes here, so we're talking very compact accelerators, right? And so in fact in the gamma rays, you see these active galaxies, that's part of what inspired this idea. These active galaxies make bursts of photons in like minutes, where the light comes out, and the idea is that maybe the accelerator at work. I mean, this is not first of all, I'm not the right person, and this is not a talk about speculations on astrophysics. I'm a particle physicist. Any other questions? So does this answer your question? Yeah. Yeah, so you can think of all of this happening in a straight line. Yeah. Yes?
I think you mentioned that the cross-section for interaction for neutrinos goes up with energy.
Yeah.
Could you
Uh,
elaborate on that?
yeah. In fact, I can use this, right? Who's going to stop me? Okay. This is the neutrino cross-section as a function of energy. And so it looks like this. And so, as I will tell you later, I mean, the probability that you detect a neutrino, the neutrino has to hit a nucleus in your detector. In the case of ice, it has to hit hydrogen or oxygen, right? And in the case of water. So the way it rises is, if this is 1 TeV, and this is 1,000 TeV, this is about the energy we are interested in. So here, it rises as E square. So the probability that you detect a neutrino, 10 times higher energy is 100 times easier to detect. That's how it works. At 1 TeV to 1,000, it's kind of linear. It's a to the 1. And after 1,000, it goes kind of as, you know, it goes e to some power. In fact, what I'm telling you here is the neutrino cross-section times the range of the muon. It's a detail. But so as your detection probability is proportional to the cross-section, you see higher energy is much easier than lower energy. Yes?
Which energy you mean here? Energy of neutrino or
Energy of neutrino. No. Energy of the neutrino in the lab. The one that's relevant to me.
then the energy in the center of mass?
Hmm?
Okay. Well, if there is TeV energy of neutrino
In the lab.
in a lab, in
Yeah.
the center of mass, what is the relevant energy?
Oh, you can work it out, right? Yeah, we can do it over the break. 2m S is 2m E nu. So, yeah, these numbers are not quite right. They are a bit exaggerated because they include the muon range. This is correct. This is almost correct. This I don't remember. I shouldn't quote anything here. But there are two ideas. It gets easier and easier, and the idea is at higher energy you don't gain as much as at low energy. The thing flattens out. In fact, it goes as the log cubed of the energy in the end, which is theory, and it's probably even true. Okay, other questions? No? Yes?
I was wondering, how do you determine the magnetic field strength of a supernova?
You don't. First of all, for my neutrino calculation, it doesn't matter. Remember, I don't care. I mean, the photons tell me what... If you want to make a model of the supernova remnant, and you want to explain why there are so many TeV photons seen by the astronomers, then you have to build an accelerator, and then people debate forever what this magnetic field is. But I don't care. I know how many protons supernova are supposed to explain, and I know the density of the molecular clouds. I can go and look these up in an astronomy catalog. And that's all I need. How the protons get to TeV and produce TeV pi zeros, that's an astronomy problem. In fact, it's a very difficult problem. While I'm on this slide, this is not the subject of my talk, but is anyone here in this room who has studied shock acceleration ever? Stuff, huh? Well, if you take textbook shock acceleration seriously and you put in the values for supernova in our galactic, in our galaxy, you actually you run out of energy somewhere here. You cannot even explain the high end of the cosmic ray spectrum. Then people invent all kind of additional ingredients. You know, nobody has ever been there, right? So you can add whatever you want. And so then you have to, it's like you have to say the magic words and then the energy suddenly go up. The truth is that in this energy region, which by the way the cosmic neutrinos come from that we have detected, in this energy range, we have no clue how these particles are accelerated. We don't even know whether it's extragalactic or galactic. Everybody believes it's galactic, I don't know why. But anyway, but this is nice, right? I'm not criticizing. This is a beautiful field. You know, I come from a field, the last thing I did in particle physics was do 2-loop radiative corrections at LEP. And you could calculate everything, and it was even correct. You do the experiment, it's confirmed. And so this for me is like a liberation from the prison. I like the prison too, by the way. I would gladly go back and do particle physics. In fact, I still do. Yeah.
So I'm trying to have a feeling why...
Oh, this is recorded. Yes. I can make a lot of enemies in a short time.
Why this is this trend of the cross-section?
Why is?
Yeah, the reason for this trend, for the neutrino cross-section?
That is not something I'm going to explain, I think, in few words. But, okay, the reason is, you know, the neutrino interacts, this is a neutrino proton cross-section. So a neutrino, you know, mostly ignores anything. Unless it hits a nucleus head-on, you won't see it. And so the nucleon, the proton, is made out of partons. And the higher energy, the basic answer is that the higher energy the neutrino, the shorter its wavelength. And short wavelength neutrinos see lower, softer partons than a low energy neutrino. And so the higher the energy, the more soft partons is seen. And that, in fact, the cross-section, the parton cross-section grows linearly. Yeah. And so that's this is well understood. So all the physics in this experiment is standard model physics. So I learned this in prison. There's no problem. Any other questions?
I have one.
Yeah.
You mentioned that you don't believe that those neutrinos originate from pulsars.
Oh, that,
Then you mentioned that.
I shouldn't have thrown, no, I don't mean,
Why can you?
what I mean here there is a pulsar involved too, because it's the gravitational collapse to the pulsar that releases a solar mass of energy that makes this accelerator. What I mean is where the rotating pulsar itself accelerates the cosmic rays. It's not impossible. In fact, Olinto, who's a astrophysicist at Chicago, she has made like arguments that this may be possible. You could make all the cosmic ray, galactic and extragalactic, by pulsars.
How does it work?
Not really all of them in the galaxy, but some of them. It's you have a fast spinning magnetic field. It's a dynamo. So that's it. Pulsars are easy to understand. The thing is they spin down and they are questioned whether they really live long enough to get the particles to high energy. It has to happen, the acceleration happens in extremely short time. And it's possible. So it's just a dynamo. That's much easier to understand. It's a rotating magnetic field. You get an electric field, you accelerate particles. So this is much easier to understand than shock waves. Yeah. Okay. Now I have to go on. Although, you know, we are... So neutrinos associate with cosmic rays. I already discussed this. Gamma ray bursts make cosmic rays. Cosmic rays interacting with the microwave background. So, and supernova remnants. And so I, first of all, concentrate on this slide. And there's something you have to realize when you look at my plots. That is that shock acceleration or reconnection, all these models, they tell you that the number of cosmic rays as a function of their energy has an energy dependence of something like 1 over the energy square. So you go a factor 10 higher in energy, you have 100 times less particles. So what I always do, and what everybody always does, I plot E square times the flux. The flux is the NDE, the number of particles. And you see that's a constant. So all the predictions are constant lines on this plot. And so you see here, this is kind of the band of predictions for supernova remnants, the galactic cosmic rays. And you see this band goes on in energy. I don't know where it stops. That's my remark about shock acceleration. It may stop here. It may go all the way to where the extragalactic come in. This is the calculation for gamma ray burst, 1 neutrino per neutron. Here. This is the calculation. This is the green band. Okay, so this is just a compilation of everything I told you. Now, what's this? This is the flux of atmospheric neutrinos. And this is the problem with neutrino astronomy. If you look up in the sky, you see neutrinos. In fact, IceCube sees 1 every 6 minutes. You wish you didn't. So what they are doing is when cosmic rays, the same cosmic rays you saw in my first 2 slides, when they arrive at the atmosphere, they hit the nitrogen and the oxygen, makes pions, and the pions decay in neutrinos. And so there are, if you look up at the sky, you see enormous numbers of neutrinos coming at you. And so these numbers, this is again one of these logarithmic plots. So here you see this is 1 GeV neutrinos. And then when you go higher and higher in energy, that's a measurement of the cosmic ray flux. No theory. We can calculate this. But you don't need to. We have measured it. So you see Super K there, Frejeux, Amanda. Amanda is the R&D project that led to IceCube. And so you see the conclusion of this whole discussion is once you come to this place, you see this flux dives under your prediction. So if you go to high energy, you don't see atmosphere anymore. And the magic crossover is 10 to the 5 GeV, is 100 TeV. And the experiment has reached it when this plot was made. So now it's clear, if any of the stuff I told you is true, you go that way. If it's not true, you keep measuring this way. There's another way to look at it. There's 100 TeV neutrino per year in IceCube. If you see 10, you have discovered some of higher energy. If you see 1, 10 times the energy, you may doubt, but you've almost discovered something, in fact. So what is this? This is something like 10 to 100 neutrinos per year. Okay, so now I have 10 minutes left. So this is nothing new. This is a summary of where we are. How do you build a kilometer-cube detector? In fact, this doesn't go back to the 50s or the 70s. This, in 1960, I like to show this picture because most of an incredible number of ideas in neutrino physics is due to the man on the right, who's Bruno Pontecorvo. This is the man who had this idea, however. He realized how to build a kilometer-cube detector. And so this is how you do it. What he proposed, in fact, they built such a detector in Lake Baikal, a small one, which they are now trying to expand. But the original experiment that tried to do this was off the coast of Hawaii. You imagine you go 4 kilometers deep in the ocean. Where it's dark, you have ultra clear water. And so imagine a kilometer cube of water. And the water is the detector, so you have to instrument it. So you fill the kilometer cube with photomultiplier tubes. Now for the theorists in the audience, I don't want to insult your intelligence, but this is the photomultipliers that, the workhorse in this field. It's something that it's 20 centimeter, it's like a basketball, and it detects 1 photon at a time. And so you put many of these in this kilometer cube, and then you do what I just said. So then, if you have a neutrino, and look, I know it's a neutrino because it came through the Earth. Nothing else comes through the Earth. So if you see a particle that you detect from below your feet, it's a neutrino. If it interacts, a neutrino you don't see, it has no charge. But if it hits a proton head-on with this cross-section, then it makes charged particles, electrons, positrons, everything, all the particles we love, pions. And these pions are charged, and they radiate light in a clear medium, Cherenkov radiation. So it's the same, it's actually mostly blue, the light. When you see pictures of reactors that are covered with water, the water always has this blue glow. That's the Cherenkov light. These are charged particles coming out of the reactor in the water. So that's how you detect a neutrino indirectly. Now, even if the neutrino interacts a kilometer outside my detector, at these energies, if it's a muon neutrino, it will make a muon, and muons at this energy travel kilometers. And so if the muon reaches your detector, you have a beautiful picture. You have this muon goes at the speed of light through your detector. It leaves its wake behind, which is the light, which moves at the speed of light divided by the index of refraction. So just like a speedboat that goes faster than the speed of the waves on the water. And so your photomultipliers make a map of the Cherenkov cone. You know the direction of the neutrino, of the muon, and at high energy, the muon and the neutrino, remember, at these energies, everything happens in a line, right? And so, important, all the physics that goes into the analysis of the data is either electrodynamics or standard model weak interactions. So all the physics is known. Okay, so this is a cartoon. Well, no, this is an actual simulation. This is a muon going to the detector. And you see the Cherenkov wave spread out. And the photons interacting with the photomultiplier tube. And so so once the muon goes through, all these colored dots is what you're left from. So what are the colored dots? A dot like this is one photoelectron detected. A big dot like this is maybe 1,000 photons. I don't know, 100 to 1,000. And so you can think of each dot as two numbers, a time and an amplitude. And then you can reconstruct the event from those two numbers. We're actually doing better now than that. So do you get the idea? Very simple idea. And except that that's not really how it works. This is a simulation of a muon. And you see this hair growing out of the track. Those are the photons. They scatter and then eventually they get absorbed. But you see, the light doesn't come uniformly like in my simulation. It makes these bursts of light. So what's that? So there is really no Cherenkov cone. You have to look very hard to find a Cherenkov cone. What you are looking at is a muon of TeV energy. What it does is, of course, it's still minimum ionizing, but it will radiate a photon. And then a bit further, it may produce an electron-positron pair. Then it may interact with the nucleus in your water. And so those are these balls of light. So each time the muon does something catastrophic like this, it will emit this ball of light. That's what you were looking at. And the higher the energy of the muon, the more it does this. So you can kind of count balls of light, or simply count total number of photons, and it's a proxy for the energy of the muon. And the muon, of course, remember the energy of the neutrino. That's standard particle physics. So now we can do an energy measurement, and you will see this is absolutely critical. Okay. Let me skip this. So the only thing we did differently, when the experiment in Hawaii was failing for technical reasons, it's not easy to put thousands of photomultipliers 4 kilometers deep in water. They deployed one string of photomultipliers. It lasted 24 seconds, and that was the end of the experiment. So our idea was to freeze photomultipliers in the ice. By the way, it's called Dumont experiment, and this experiment pioneered practically all of the techniques that we are still using. They just started this a bit before the time of the technology being ready. There is an experiment that perfectly works in the Mediterranean right now, called Antares. So at the South, why are we at the South Pole? There is a station with bulldozers, cranes, people's beds, a hotel. This is the runway, so you have planes to bring your equipment in. And this is IceCube project. And so what we first did was build a small detector, which was called Amanda. If you don't mind, I'm going to go a little over time, and then I want to go to bed. I will stop at 10. So we built a small experiment with 700 photomultipliers and showed that it worked, that we could detect atmospheric neutrinos. And so you can see this is a picture of the South Pole in the year 2000. That's the geographic South Pole. And about 800 meters away, you go 1.5 kilometers deep, and that's where we have the photomultipliers. This is the house that holds the electronics and the computers at the surface. And then you go and ask for money, and we built, now you take a kilometer cube of ice and you fill it with 5,160 photomultipliers. That's what we did. And you will hear tomorrow how this detector works. I don't want to go into all the detail, but this kind of, it works beautifully. They're almost like a CERN experiment. The hard parts of this experiment was to put this stuff in the ice. And so we had this system of car wash heaters, about 40 of them, and that pumped water into this hose, which you see on the reel here above. That's a 2.5 kilometer long hose, this big. And so there is a nozzle on it, and you let it just fall under gravity in the ice. And while it falls, you push out hot water under pressure, and it melts the ice. It turns it into water. And so after 2 to 2.5 days, you pull the thing out, and you have 2.5 kilometers of water over this volume. You lower the sensors into it, wait until the water freezes, and that's it, you take data. And so that's what the system does. You see, it's like a bomb, it's a 5 megawatt jet of water. So here you see the hose coming, the drill coming out, and you see there are 60 photomultipliers waiting. They are in pressure vessels, and they have some other paraphernalia. But so then, here this is the cable. Remember, this is 2.5 kilometers of water. So every 17 meter, you attach with carabiners a photomultiplier. Notice this is the photomultiplier. They point down. We're looking through the Earth. And so then you lower, 17 meter higher, you attach another one. And when you have the 60 finished, you have a kilometer of instrumented on a cable that bring in the high voltage. And that also brings out the signals. You should not forget to plug it in each time. So then there is a 600-pound weight at the bottom, and then you just let it go, and it sinks to 2.5 kilometers. You do this 86 times, and you have IceCube. You have a kilometer cube instrumented. This I don't have time for. You have to know the optical quality of the optical properties of the ice, how photons propagate. You saw this hair growing out of the track. You have to understand that. And this took years. Every module actually has 12 LEDs in it of 3 different colors. So you can calculate times 5,160 how many LEDs. And we shoot these LEDs from every module to the next. And this is the way we find the optics of the ice. We have lasers in the ice. There are other paraphernalia. And so what you want to know is, as a function of depth in the detector, the absorption length and the scattering length. And this is a magic number. You cannot produce in a lab a solid that has 220 meter absorption length. And why is this so clear? It's because it's 100,000-year-old ultra-pure condensed snow. There was no pollution, nothing. And where there was pollution, this happened. This is a bit of dust that came from South America and mixed with the snow. By the way, this is still pretty clear, actually. This is still clearer than distilled water, even in the bottom of this peak. We actually have measured the ice so well that in part of the detector, geologists knew there was a period around this depth of very intense volcanoes. And people had looked in ice cores, had never seen these volcanoes. And look at our data, you know, here it is. It's called the Toba event. So these volcanoes are about just under a centimeter of dust. This doesn't go into photon propagation. Okay, so here's a picture after 2 months. 20 strings have been deployed. These strings go into this house, and this house contains all the computers that analyze the data online. I'm going to stop here. I'm going to go on a little bit. It's a pity to rush through this. We have time, right? It's not... any questions? Yes?
How do you align them?
Ah, very good. How do you do, and that is absolutely critical. you know, if you don't know where your module is, every meter is 3 nanoseconds, the speed of light. And you want to do as you will see later, you want to do nanosecond timing. If you don't know where your module is, every meter wrong is 3 nanoseconds. Any way you can. I mean, we track the drill, which is not very easy. That gives you maybe a 5 to 10 meter precision. In fact, the holes in the end were over 2.5 kilometer vertical to within a meter or 2, 3. Some holes we didn't do that well. But after the fact, the answer is you shoot light from one to the other. So when you determine the light properties, think of it as a huge fit to photon propagation data. Where the modules are become part of the fit. That's the easiest way to think about it. We are still doing this, by the way, as we improve. Any other? Yes?
The part below is moving a bit, and this creates some...
Oh yeah, the detector moves between 10 and 11 meters every year. But it's sitting in a glacier, right? That runs off the West Antarctic mountain range. And so it moves uniformly, so it doesn't matter. We are trying very hard to see any deformation in the ice. Not that we care, but the glaciologists are very interested in this. And they have, you know, nobody has ever instrumented a kilometer cube of a glacier. This is an incredible experiment for them. We actually have tilt meters. On one of the 86 strings, we have in each module a tilt meter. But so far, we haven't been able to detect anything. And I think it probably is because people begin to think, you know, there is a network of lakes and rivers under the whole Antarctic ice sheet. And they are connected to the sea. And so this is like a hydraulic system on which the ice moves. And so that explains. If it were attached to the ice, it would be different.
How thick is the ice there?
3 kilometers, sorry, I should have said that. So 1.5 kilometer deep, a detector 1 kilometer, and then there's 500 meters left. I didn't tell you that, yeah. So the ice was just right to make a kilometer cube detector. We were worried about going close to the bottom and having, you know, the strings deform, and we worried about that, but there's actually no problem. Even if they were shear, it's mostly tilt, and tilt doesn't destroy the strings. I saw another finger, so, yeah.
But the ice can destroy, I mean, the way the water flows.
Ah, yeah.
It flows in different ways. I think,
Yeah.
for different
Well, that's why you don't put a photomultiplier in this whole. Everything, including stuff I haven't talked about, I will talk about here, is in 2 half spheres, which are a centimeter, about a centimeter thick glass. And so every module is tested to 10,000 psi. And so when the ice refreezes, it refreezes by fingers coming out of the walls. And then eventually it forms pockets. And in these pockets, then they eventually collapse to solid ice again. And there are huge pressures at that time. We think 6,000 to 7,000 psi. And so we actually deployed TV cameras. And so this is very exciting. You can go to our webpage and look at hours and hours of a TV camera looking at a hole in the ice. But what you see, there's one exciting moment. Because the TV camera goes down and it goes to snow. The first 80 to 100 meters of the surface are snow. And then so what this camera does is, you have a light source. so that it can look into the ice. And in fact, we can turn it. It's very exciting. So then when it comes to the solid ice, it suddenly becomes clear. There's no snow anymore. And so suddenly the picture turns dark. Why is that? The light just disappears in this clear medium. And so the only thing you see is this little bit of dust reflecting the beam. But why we deployed it was not, we actually looked, you have melted the ice, which means you have released a lot of oxygen in these bubbles, in this ice. And when it freezes back, we wanted to know where the bubbles were. Guess what? The ice is perfectly clear. They all sit in a little column in the middle. And then if you wait maybe 100,000 of years, these bubbles will collapse, but they are there. And so we are just reaching the precision in reconstructing photons. Remember, bubbles over this distance, when your modules are 125 meters away, is not much ice. So they play a very little role. It's a very small effect. But we begin to become sensitive to it, so we are studying these bubbles. And if we are thinking about building a bigger detector, and we would actually make sure that we get the air out of the water before it refreezes. Yes?
You several times mentioned that your measurements are improving. Since there's no way to improve your equipment.
It means you understand the ice better and better. Yeah, I mean, the detectors, you live and you die by how well you understand the propagation of the light, right? I'll give you an example later. All right, so I stopped at this point because this is a little bit of technical, because I think it's interesting. When we did the demonstrator experiment Amanda, every photomultiplier was connected to a cable. In the beginning it was coax, at the end twisted pair. And so you send a high voltage to the photomultiplier over the cable, and then the signal that came out of the anode of the photomultiplier was actually sent back to the surface over that cable. And so, a signal that travels over 2 kilometers of cable doesn't look very pretty. And so the idea was now in IceCube, every photomultiplier, you see this is the photomultiplier, the picture is difficult to see, so it's pointing down, right? So the photomultiplier is here. This is the neck of the photomultiplier, and this is a data board that you see there. And what that data board does is, when the signal comes out of the photomultiplier, it's caught with a chip, doesn't matter, and a flash ADC and 2 chips. But what it basically means, and you have a computer, a PC, that makes a digital image of the signal right there when it comes out of the photomultiplier. This digital picture is then sent over the cable to the surface, and no information is lost. So that was a big piece of progress. And so that's this data board. So what it means in practice, it means you have a totally different experiment. So there's no IceCube. There are just 5,160 optical modules. And so when an optical module detects light, it digitizes the signal. So this is the number of photons as a function of the number of nanoseconds. So this is what it sees at that particular time. And then we have a system to tell the time to each module to 2 nanoseconds. The way you have an oscillator at the surface, and this oscillator bounces signals back and forth to each module continuously. So you send like a theta function, you send it, and it sends theta functions back to you, and you match them. And so you can tell time across the whole absolute time to 2 nanoseconds. And so a module detects light, it makes this digital picture, it puts a timestamp on it and sends it to the surface. And so the computers at the surface collect these messages from all the optical modules continuously, and then they build them into neutrino events. And so I'm going to show you how this works in the next slide, but before I show you the slide, I have to tell you something. Remember, at the South Pole, we are looking for 10 neutrinos a year coming through the Earth. That's the. However, your experiment is 2 kilometers, 1.5 kilometers under the ice. Now, this table, the cosmic ray muons, the ones we are not interested in, when the pions decay in the atmosphere, they make neutrinos, which some of us are interested in, but the muons we are definitely not interested in. These muons go through this table at about 150 or so every second. Now, if you go 2 kilometers deep, there are less of them, but you collect them over a kilometer square of detector. So you have this huge range, this huge rain of muons. And yes, they come from the wrong side. But the only way to tell that they come from the wrong side is by reconstructing them. And so you cannot do this. If you make too many mistakes on this, you cannot tell up from down. You cannot find neutrinos through the Earth, because a muon is a muon. A neutrino is a muon coming up, and a cosmic ray muon is a muon coming down. If you cannot tell up from down with a precision of I think we now make about probably one mistake in 100 million events. But if you have to do that, it's not, otherwise you have a background that kills you. So after this being said, this is the detector taking data. And so you now know what you're looking at. You see these colored dots appear. That's each time a module sends a light signal. And you see it arrive at the right time. And you see all these tracks. Those are the computers fitting tracks to these messages. And you will see the thing reappears. And you see overwhelmingly, these are, now it starts over. How long do you guess this movie is? You cannot tell. Anyone wants to make a guess? It's a lot of data. 10 milliseconds. You were 10 milliseconds. So this is the problem. So atmospheric muons coming from the south, we have about 100 billion per year, 2,700 per second. In the summer, this is 3,000 per second. In the winter, it's less. This is because in the summer, the atmosphere expands. And so then the pions are most likely to decay into neutrinos and muons rather than re-interacting in the air. And so anyway, your target, think of it as your target changes and you get different numbers of muons. We actually see, when the daily variations of the temperature we can see in this muon rate. And in fact, in 2002, we suddenly saw muons disappear for several days. Not totally disappear, but there weren't enough, and the detector was working. And it took us 2 years to figure out when finally a German student discovered that we saw the ozone hole breaking up. So your target disappeared for a few days. And so this is the type of things you have to deal with. Now, atmospheric neutrinos, they are interesting. They are neutrinos, it's a beam of neutrinos. We see one every 6 minutes, so it's about 100,000 per year. So really high quality neutrinos, when you throw all the doubtful ones out, we have about 50,000 per year that are really high purity. You know, much less than 1% is background. 99 point something are true neutrinos. And then I have already told you we're looking for 10 events, 10 to 100. So you would think this is impossible, but it isn't. So this is a neutrino. This neutrino has about 100 TeV, and you see it goes, red is early, you follow the rainbow, the color tells you the time. So red to blue is early to late, so the muon track comes through the Earth. Now, when you see a lot of photons, you have to be careful. That doesn't mean you had one of these catastrophic energy losses. It often means that the track came close to a module, and then it has more photons in it. But that's useful information, right? So this is the 100 TeV muon per year or so that you expect in IceCube. And that's the talk for tomorrow. But I'll just show you, last December we published, in fact we found these 10 neutrinos per year. We actually didn't find 20 in 2 years, we found 28 in 2 years. And I'll show you one event. Before I'll show you the event, let me tell you, how do you normally look for neutrinos? You normally look for neutrinos, what we do is, every neutrino you detect is a point in the sky. So a neutrino, well, if you're in the north, you look at the southern sky. So you see a neutrino come from there, so you make a map of the southern sky, you make a dot. And if you have enough dots, you hope to see clusters of events appear. And these clusters is where there are sources of neutrinos sitting on top of this uniform background of 6 atmospheric neutrinos per minute. And so this was the Amanda demonstration. You see the map on top. It was shown at the weak interaction meeting, in fact, in 1999. This was a big breakthrough. We saw 17 neutrinos, and we already made a map of it. When the IceCube was half complete, 59 strings, this is the map. We now found a way to look up, but I won't go into that, and down. But that's the last map I can show you, because after that, this map just turns black. The resolution of PowerPoint is not good enough. So these are just black maps. Now this map are the 28 events I will talk about tomorrow. They are cosmic neutrinos. They are not produced in the atmosphere. We know it because we did a different analysis from this one. We'll discover cosmic neutrinos this way. Eventually is within months. We now know what to do. And but at the moment we did a special analysis, and I just, in case you want to sleep late, I'll show you one event. Now you see this event? So the light starts here, then travels out to the next strings. And here, you see this, you see that, up, that's a muon track. And so you're looking here at a muon track which emitted this enormous amount of light in the bottom of the detector and then happily traveled on. It's a bit of a strange event. It's one of these 28, because the muon track looks like it's 10 TeV from having looked at thousands of 10 TeV tracks in the last 15 years from Monte Carlo. This looks like, it is enormous energy, I've forgotten. But, when I look at this, I know it's something I've never seen before. I know what 100 TeV events look like. So these events have typically, we have, remember, one event per 100 TeV per year. Now we have close to 20 that are are above 100 TeV. And so you actually, if you plot the data as a function of energy, you just see the events stick out. So finding them was easy. The critical thing is that you can measure energy very well. And so this is a set of events that have more than 100 TeV, most of them. And so that's how easy it is. In fact, now, after seeing it, I just gave a colloquium in Nijmegen, I can just plot the events and everybody can see the signal for themselves. And there's no analysis involved. So where they come from, we don't know. That's another interesting thing if we go back. Yeah.
How do you measure the energy?
The energy is just the amount of light. It's how big this ball of light is.
Somewhat.
You know, this was a photon that was radiated by this muon or an electron-positron pair, and then it cascades in the ice and it makes light. And in fact, how do you, the simplest way of measuring the energy is, when you get used to look at these events, if you take an event that's 10 times lower in energy, it becomes 50 meters shorter in radius. So every 50 meters is a factor 10 in energy. And we can do this. And because the optics in the top or the bottom of the detector is different, you have to be a bit careful. You know, the optics is the ice is so clear that things that look big in the bottom are not necessarily very energetic because the ice is so clear. So you must be able to, but you know, this is not how we do this. I can do this by eye and many of my colleagues can, but you know, this is done professionally. And I will explain tomorrow, we cannot even tell the direction. So, but here is so this is the first map of cosmic neutrinos. So the question is, what do we see? Do we see gamma ray bursts, supernova remnants, active galaxies? The truth is we don't know. These are only 28 events. And you see, this line, this is equatorial coordinates. So this is right ascension and declination. No, declination and right ascension. You see, I'm not an astronomer. This is the plane of the galaxy, this line. And so this is a muon neutrino that could have come from the plane of the galaxy. You now all see this blob. This blob is very close to the center of the galaxy. So, but you have to be very careful. This blob has, in this blob, you expect, if this were a uniform map, you would expect 0.65 events. Less than one event, and you see 7. You say, this is it, you have discovered something close to the center of the galaxy. But that's only true if I had predicted that I would see a source there ahead of time. Once you realize this can appear anywhere in this map by accident, the probability is 8% that this is a background. So it's 92% source, 8% background probability. That happens all the time. You cannot publish things that are 8%. You're going to get burned most of the time. Another way of looking at that, you know, if you have a map like that with 28 events, and you take another 28 events, we have actually doubled our data since this paper, since this analysis. If you double the number of events, this map can very well look totally uniform. I've seen this happen in the past. You know, we've been playing with maps since 1996. So you just have to wait. We'll have more events, we have more data. We'll have muon neutrinos, which we can reconstruct very well. These are mostly electron and tau neutrinos. Yeah?
I'm a bit confused. How is the galaxy on that map?
Oh, look, as I'm running out of time, I'm not going to start a new subject. I'll show you. You can ask me questions now. I'm not going to give tomorrow's talk, but by the way, if you don't know what a kilometer cube detector is like, let me show you this slide. If any of you has visited University of Wisconsin-Madison, this is the campus, which is along a lake. And that's the size of this event. So if you realize this, so take whatever your hometown is or your home university town and imagine 6 city blocks. That's the size of the event. Now this is important. This is not the event I showed, it's a different one. In fact, I may as well now go and show you a few slides. It's a pity that you wouldn't know what the outcome of this is. So let me, okay. So this is a simulation of these blobs. Because you say, you know, in fact, this event, there is no mu on track. It's just a blob of light. And you see two things. Remember the color, these are the photons, and the color is time. So you see here, these move faster than these. So although the blob is totally spherical and uniform, if you look at the times of the photons, they are very different. They are different in, you see there's more yellow here than there. First there is more red here than there. So now, what is this? There's no mu on track that I've been brainwashing you with. Well, what it is it's. Let me go back to this slide. This is an electron neutrino. It's not a muon neutrino, or it may be a tau. We cannot tell that. So what happens now is, this is obviously, remember the event started in the detector, right? So you see here, the electron neutrino interacts. What does it do? It gives 80% of its energy to one electron, then there's some other stuff. That electron begins to shower in the ice. So you get a splash of charged particles, and they emit this blue light. Okay, so that, and now the key point is that this shower is very small. In fact, I think that on the next slide, this is a simulation of a neutrino, an electron neutrino of this area interacting. So the whole volume is 5 meter cube. So 5 meter cube of ice in a kilometer cube of ice is just a point source of light. You don't see any direction to it. It's just so small, 5 meter cube. On the other hand, if so it's the size or less than the size of this room. On the other hand, if the neutrino came from there, the shower developed in that direction. And so the photons it radiates will come out sooner there than in the back. And that's what you saw when you looked at the colors in the simulation. So the times, the size tells you the energy, the times tell you the direction. So it's a whole new technique. Questions? Got this? In fact, 2 of these 28 events were discovered by accident. We were looking for something else and then saw these 2 events. You know, we do blind analysis, so everything we look for, the whole analysis is done on simulation. Then we take 10% of the data, verify the simulation, and then we, is what you call open the box and look at the other 90% and look what's in it. And so we were looking for cosmogenic neutrinos, my first slide. Remember 100, a million TeV neutrinos, and we found 2 of these events. And you can say this is not, a million TeV, but it was 10 times more than the 100 TeV we typically see as the last atmospheric neutrinos. So then, we had to learn how to reconstruct them. So let me see what else I'm going to, okay. So, and now this is where the fact that we count photons, you get these messages. So in Amanda, a dot like this was just a number of photons, a guess on the number of photons, and the time. But now each of these dots is a detailed distribution of the number of photons detected by the photomultiplier as a function of nanoseconds. And so I'm going to take, so in this event, which is the event I showed, in this event, I'm going to take one photomultiplier, which reported that signal there. And so, of course, if you fit the event, you fit the times, you get the direction, the energy. And so the blue line, is the fit to the event. And the red line is if I turned the neutrino and the shower around by 180 degrees. So you see from this one photomultiplier, you can already tell that 180 degrees is not a good guess. But then you have more than 300 of them in this type of event. By the way, there are 100,000 photons in these events, typically. And so we found these 2 events. Remember 100 TeV? These were more than 1,000 TeV. We actually could have claimed these events. But so as evidence for cosmic neutrinos, we didn't. We published them. But then, we saw the advantage. As energy is kind of the key to move out of the atmospheric background. Remember my slide where the atmospheric background went down and you want to find events at high energy to the right. There was the key. We start to look for more of these events. And so it was very simple. What you do is what Super Kamioka and every neutrino detector does. You divide your, this is IceCube, and you divide it into an inner piece, which is your active volume, and a veto. So what it means is a neutrino is when you see an event start in the detector, like we saw on the animation, the event starts in the detector, the light either propagates, and you see no light coming in. If it's a muon, if this is a muon, that's an atmospheric muon, it would have produced light here. And so this way you select these events where the neutrino interact. You have a 420 megaton detector. That's the bottom line. And you can do something else. If this were an atmospheric neutrino, then it's introduced in an air shower. So it's produced in an air shower, and it comes with a muon, because the pion decays into a neutrino and a muon. And in fact, it comes with the muons of all the other pions created in that air shower. And notice these events are a neutrino and nothing else. So this veto will also veto showers. If there's a shower and puts a muon through, then there may be a neutrino, but it's atmospheric. We throw it away. So cosmic neutrinos are neutrinos start in the detector and are not produced in an air shower. And in fact, one of the 2 PeV events, the first 2, a PeV, by the way, is 1000 TeV, 2 PeV events, one of them came from there somewhere, and so it came close, but at the South Pole, so it came from the southern hemisphere. It came close to the air shower array that's on top of the experiment, and you could go and look in the air shower array whether there was any evidence of an air shower that was produced at the time this neutrino came through. There's nothing. Absolutely, not even a single hit in one of the scintillators that make up the array. And so, I mean, we, instead of working hard on these two events, we found more. So this is the bottom line, kind of. So what this plot, you know, if you shows the effect, it's a three-dimensional plot. The vertical axis is the number of events. The horizontal axis is the number of photons in the event. So a lot of photons is high energy. So in this direction, you go to higher energy. What's this axis? This is the critical one. This axis shows you the number of photons in the veto layer. And so, of course, what you want is no light in the veto layer and a very high energy event. So the interesting events are in this corner. All the other events are here. And you see in this plot, this is 1 year of data, all events. So you see this, the events disappear, but then look here, you see these events sticking out. And you see there's no analysis, you just plot the data. And you know, you thought 10 events a year, they'll never find this. You just have to plot the data. So this energy, and the critical thing is that people built this beautiful detector that can measure energy to 10–15%. And that's the key. So now what we actually did was a blind analysis. So we did the analysis on the simulation, and we required, our final cut was, we looked for events in this box. That was the signal box. And it meant less than 3 photons in the veto region, and more than 6,000 photons in the event. And then, of course, no accompanying muons and stuff like that. And that meant that if you, in this box, there are about 4 background events per year, but the active volume is 98% efficient. So you only lose 2% of your signal, but you have a background of 4 events per year. And so if, you know, now you can count. And so this, the next slide is...
Sorry, may I ask?
Yeah. No, it's, I mean, I'm happy to spend the last 10 minutes just on this plot. This is the, what do they call this? The money plot. Sorry, who? Yeah.
Why are those events there? There's this line, the red line.
That's the sum of all the events.
Ah, okay.
So if you sum this, you get...
So it's projection.
It's a projection of the sum. Yeah. So that are all the events in 1 year that we detect. Yeah.
You didn't get well how you get rid of the atmospheric neutrinos.
Okay. So maybe a picture helps. This is the ice. This is IceCube. This is the atmosphere. They are produced, cosmic rays come in, and at a height of about 20 kilometers, the cosmic rays interact with the nitrogen and the oxygen in the air. And so you have a cosmic ray. It makes pions. And the pions decay in a muon and a neutrino. And of course, I draw it this way, but remember all this is like all aligned, right? This huge energy, everything is boosted with a large Lorentz factor. So there's no, I draw as if this spreads out, but it doesn't. And so you see, if you suppose this neutrino, you don't, yep, and it starts an event in the detector. it makes a muon track, or it makes one of these balls of light. It looks exactly the same as a cosmic neutrino, but the difference is that it's produced with a muon. It doesn't come from some source far away. And so this muon will also go through your detector. So if you see a starting neutrino with a muon track, it's not cosmic. You've tagged it has an atmospheric background. In fact, the other pions you produce in the event can also make muons in the detector. So this is pretty efficient way of vetoing. So all these events have been subjected to this. Yeah.
But, I mean, the atmosphere is all around.
Yes.
So if the cosmic ray comes from another direction, so we have atmospheric neutrinos that goes from here. So we see only the neutrinos. So how we can say that this is from.
Yeah, then of course there is the chance that the muon got absorbed along the way. So this has a certain efficiency. It's not a guarantee. That's part of the background. So you are what you mention is an example of a background event that we could mistake for a cosmic neutrino.
Yes, but what is
Yeah.
the rate? Because the rate.
Well, the rate is that we get 4 events. We actually see 4 after the fact. We predicted 5 events per year that are due to problems like this. This is not the only one. You know, there are, by just fluctuations, right? The most important veto is, of course, all these muons coming down. So that's a layer of 6 photomultipliers. And so after you open the box, you go and look at each event. First of all, you can clearly see whether it started in the detector or not, after the fact. You can see whether there's a mu in it or not. But what we then do, you can go and look back whether there is any light in the veto. And then sometimes we can actually, some of the events actually have some light in the veto. And so those are the background events, which you didn't. This box is arbitrary, right? So I could make this box smaller, and then I would have no background events. But then I would have less signal too. So this was the box that optimized signal to background based on the analysis done with the simulation. Any other questions? Yes?
So you mentioned the size of the event scales with the energy.
Yeah.
So
So where that's important, right? So you can look over these times, the times being different of the photons traveling in that direction. You can look over these times over, literally microseconds. Remember, the time unit is 2 nanoseconds. So that's why it's so important that these events are so big. Yeah, sorry, but I answered. That was probably not your question.
So my question is then, does your energy resolution then depend on the energy of the event? If it's higher energy, then you cover.
It's pretty, I don't have a plot with me, but of course it works well once you have got a catastrophic energy loss. So for 100 GeV muons, it doesn't work at all. They're minimum ionizing every muon. But it begins to, the textbooks tell you it's, catastrophic energy loss sets in around 500 GeV. So around the TeV, it already works well. And in fact, it allows you to even below 500 GeV. So once you are above a TeV, it's 10%. No matter what the energy is.
So
And
my next question would
Yeah.
have been that would you be able to detect, now it's 1000 TeV, say you have 5000 TeV.
we were looking, remember, when we found, as I mentioned, when we found the first two events like that, we were looking for a million TeV. What does a million TeV event look like? Well, if it hit the center of the detector, it would almost fill the whole detector, not quite. You know, you add your 50 meters 3 times and you fill the detector. And so you look and you see that's not it. But it's also not like any atmospheric neutrino we had seen. And then, of course, I mean, that's not how, then you let the computers loose, right? We had 2 different groups in Madison reconstructing these events and to see if they got the same answer. One group was doing something very simple. Remember, you have to fit all these, each module, there are some 300 plus modules. Each one is a function of number of photons as a function of time you have to fit. And so you can generate all the physics that goes into this catastrophic energy loss is electrodynamics. It's all known. So you make a simulation of this light traveling through your detector. And so what you do is you just move the vertex around and you rotate the event until you fit all these waveforms. And one of our scientists, this is just by brute force, except that he found a very intelligent algorithm to make the number of trials small. It takes about, from a respectable cluster, it takes about half a day to reconstruct one event. And so we made an enormous breakthrough. This is, what you do is, after all, you propagate photons through this detector, 100,000. And each time you make a new trial for a fit, is another 100,000 photons you have to propagate. So one of our scientists discovered that, there is a way, there are computers you use for games. There are computers that do the same thing over and over again very fast. And when this is called GPUs, when we switch to GPUs, you got a factor of 150 without doing anything. And, they came just in time. Let's see. I should stop. And I'm going to show you, I just want to show you a better picture of this map. It's of course not preliminary anymore. The paper was published in Science in December. And this is the map in galactic coordinates. It's like the modules, you have to plug it in. Can you hear me again? Yeah, I'm finished. I should have done this a bit later. So you see, that's now the galactic plane. And the second highest energy event reconstruct right on the center of the galaxy, which, this is strange. It's supposed to be 1 degree off. I took this out of a theory paper. They messed it up. I have my own plot. It doesn't look, it has a mess on it, but this is correct. This is the center of the galaxy. You see, this is event 14. It's one of the 2 first events, 1041 TeV. And so this is this cluster, which you may think is somehow associated. But you see, there are a lot of events that are certainly not in the plane of the galaxy. So this is an extragalactic flux or a combination of an extragalactic and galactic. And you just need more events. We know we need more muon tracks, which we can reconstruct with very good precision, which we are getting. And so you just have to be patient and stay tuned. The worst, I shouldn't finish on this, but I'm going to. The worst possibility is that this map becomes totally uniform, which is not impossible because, you know, neutrinos, you are supposed to come from anywhere in the universe. So suppose, by the way, they are not, the times of these neutrinos do not happen at times of gamma ray burst. But they could be gamma ray bursts that astronomers don't label as gamma ray bursts. So I don't think this is that conclusive yet. But suppose we see just active galaxies throughout the universe. Then you see a diffuse flux. Then what do? Well, then you look at maps of active galaxies and correlate them with these events. So you get to the answer anyway, hopefully. So now, you know, we have our work cut out. We have to find where this comes from. Get more events and especially muon events. So that's it. Questions? So if you come tomorrow, you will hear this in more detail. But this is the punchline. You're not really missing anything. So you can go and sit in the bar.
Not really a question.
Yeah.
I guess this becomes more interesting if we combine with astrophysical.
Yeah. Since we published this paper, there are some 100 papers on the web who compare these events with everything you can think of. And the interesting thing is that the one thing they didn't think of is to combine the events with Auger events. So I did that actually, but I'm not going to show it to you. Of course, you don't see anything, right? I mean, so this is just entertainment. You have to, if you want to do this seriously, you have to find some correlation parameter which has some physical meaning, and then, so this has not happened. Yeah, so at the moment I think we just have to wait. I mean, theorists have to write papers, right? So this is a golden subject, because, but they are going to be wrong soon.
I don't know, maybe people will get
Yeah.
upset.
I'll stay here as long as you want.
So you mentioned you found a way to look up.
Only, you know the answer. It's by only looking at high energy neutrinos. So if they look like they may have a high energy, you put them on the plot because they may not be atmospheric. And so in fact, the way these plots are analyzed is that you build a probability, which is this likelihood. I didn't tell you what the color is that I showed in these plots. You see, this is a likelihood. And this likelihood, when we look up, what you do is a combination. This likelihood is large. A, when events cluster. B, when events in the cluster have high energy, which make them less likely to be atmospheric. And so for each event, you construct this likelihood. And then you compare it with a randomized map of your events. And that's the probability that you find the source. That's also how this 8% is gotten, which of course is a strange thing to do because most of these events are signal, not background. But you know, we didn't know that. So that's what we had defined before the blind analysis, so that's what comes out. We have now more intelligent ways of doing this.
So how long have you been,
Yeah.
how long have you been taking data since?
Okay, in May, we'll have 4 years of data with the completed detector. I call complete 79 strings. You know, 7 were missing that year, but it doesn't matter. And so, so we have 4 years of data. What you see here is 2 years of data. And of course, we are doing an analysis looking for muon neutrinos, which is not finished. But that will also give more events and better reconstructed events.
Can you quickly explain why the track light events have like the higher likelihood than so like when you look at the
track-like events?
Oh no, they have a better resolution.
Because you can see
You determine the resolution. The resolution on the sky of a track is still much superior to these blobs, which are electron or tau neutrinos. Yeah.
So you designed the detector to look down, but now you see mostly...
Oh, here, once you are looking at neutrinos that start in the detector, it doesn't matter where they come from.
No,
You get all directions, yeah.
well, there are many more events in
Yes,
the problem.
and that is because that's the talk tomorrow. Now you're going to ask questions until I've given tomorrow's talk. So these are neutrinos coming through the Earth. This is the southern hemisphere. At 100 TeV, the neutrino cross-section is so large that the neutrinos begin to become absorbed by the Earth. And so at 1000 TeV, the neutrinos don't come through the Earth anymore. So the signal is totally favored coming from above. And so if you do a simulation, you see exactly this ratio of events. Yeah.
But doesn't that mean that in the original design you wouldn't have...
No, remember, we still want to do muons through the Earth, right? There's still, this was designed to, the beauty of this analysis is there is no simulation involved. Even the efficiency of the veto was determined experimentally by creating a fake veto and see how much light is produced. So there's no simulation in this analysis. This analysis was designed to get a statistically meaningful signal with absolutely nothing people could punch holes in the analysis. There's no simulation. Now we go back to look for muon neutrinos, and we'll find muon neutrinos with good energy and good pointing, and we'll do better than this. Yeah, you don't want to give up on what we were doing. Anyone else? Yes?
Can you distinguish, how do you distinguish between catastrophic energy loss and general?
The minimum ionizing loss is totally negligible. All the energy loss, once this radiation sets in, you can neglect minimum ionizing energy loss. I don't think it's neglected in the simulation, but it doesn't matter. It's very small. Well, I hope you enjoyed this as much as I did. I even forgot my jet lag. Okay, thank you very much.